Okay, let's look at a new scheme now, trapezoid rule. So this I did in the last class. So here f. Okay, so I go again from xn to xn plus 1, but I compute f at 2 points, xn as well as xn plus 1. But since I'm adding, I have to divide by half. Okay, so it's some kind of average. So this is in fact is a trapezoid rule. So integral, we take the values at both ends and divide by half, multiplied by delta. Okay, now this scheme is interesting. It's a marriage of forward and backward. No, so this is forward Euler and this is backward Euler. Okay, so this part is easy. We know this xn, so I can compute f, but I don't know how to compute this one. So you need 12. I know how to do it, but it is more complicated. It is okay. So this is called semi-implicit. It's implicit and partly explicit, the semi-implicit scheme. Okay. Now you can easily see it is kind of okay. It's in the background. So here, if I do the Taylor expansion, which I'm not going to do it right now, but if you do Taylor expansion, you find that the second order term is delta t squared by 2 df by dt. Okay, so which is accurate, no? I mean, I did expand Taylor expansion of xn plus 1. Till here it is accurate. But this term is accurate or not accurate? Delta t cube by 4. Double derivative of f, which will be x dot dot dot. No? X dot is f, so I need to do 2 more dots. So is it accurate? Someone can answer me. So third order term in Taylor expansion of xn plus 1 will be delta t cube factorial 3 x triple dot. Okay, factorial 3 is 6 and I got 4 here. So it is not accurate. The difference is 1 by 12. Okay, so the error is this delta t cube by 12 x 3 dots. Okay, so this scheme is second order accurate. It's accurate up to delta t squared, but error is in third order. So error is ordered delta t cube. Okay, this is my error. So it is better than Euler. So Euler both forward and backward in terms of accuracy, and you should use well. I mean, I'll tell you more schemes. This is one of the preferred schemes. We'll encounter this scheme a bit later. So what about stability? It's quite easy to see that if you have x dot is alpha negative, then we get xn plus 1 is this. And this one is for alpha negative. You can see the denominator is greater than 1. Right? Minus alpha delta t will be positive. So denominator is greater than 1. So and numerator is less than 1 because alpha is negative. So whole thing, the prefactor alpha delta t divided by 1 minus alpha delta t is less than 1. Okay, so xn plus 1 is decreasing for alpha negative, which should. So it also works for complex alpha with the real alpha negative. So this is again unconditionally stable. Okay, so it's stable. Okay. Now, so these are the two schemes. One is implicit scheme, another one is semi-implicit scheme. Okay, and we'll encounter the semi-implicit scheme later on. I will not emphasize on it, but we'll encounter this later. Okay, higher order schemes. Okay, so as I said, we need higher order schemes. This is first order accurate, and we need to really use tiny delta t for accuracy if you want Euler forward. Okay, so let's look at higher order schemes. So remember, Euler forward or trapezoid is of this sort. So xn plus 1 is xn plus half delta t f at xn and f at xn plus 1. Okay. Now, problem is that this I need to, you can solve this equation, but it is nonlinear, it is headache to solve it. So one idea is to make an estimate of this. I exactly don't know, but I can make an estimate. And let's use Euler scheme to Euler forward to estimate this. So how do I do that? So I need this xn plus 1. No? So I'll make an estimate. It's called predictor step. So I say xn plus 1 star. Okay, this is approximate, predicted. So xn plus delta t f xn tn. Okay, and I'm going to substitute this here. Estimate, and let's use Euler scheme to Euler forward to estimate this. So how do I do that? So I need this xn plus 1. No? So I'll make an estimate. It's called predictor step. So I say xn plus 1 star. Okay, this is approximate, predicted. So xn plus delta t f xn tn. Okay, and I'm going to substitute this here. Okay, it's not exact, I know, but it's okay. I will make some approximation. So I'm just going to substitute here. Okay? And this is called corrector scheme. Okay, so via this scheme I avoid solving nonlinear equation. Okay, it is better than implicit scheme. Better, quote, easier. It's easier than implicit scheme. Okay, so predictor-corrector is a very popular way to overcome this implicit issues of implicit solvers. Okay, so stability. So we can substitute this alpha x there, and you can just do it yourself. I will not do the algebra, and it turns out the prefactor is this. Okay, and for stability, I want this to be less than 1. Now, so we make a contour plot, and so basically make contour plot with alpha as a variable. Okay, alpha delta t is a variable, and this you find the code in the book. So if alpha delta t is a parameter, then I make a contour plot with imaginary alpha delta t and real alpha delta t, and you find that this region is less than 1. Okay, and is 0 to -2. Well, it is better than circle. Circle would have gone is a bit smaller than circle, but here is slightly bigger than circle. So its stability region has expanded for predictor-corrector. Okay. Anyway, this is how we compute stability. Okay, for higher order schemes. So just to illustrate, and okay, it's a also I mean one scheme to solve ODEs. Rangakutta, which is very popular. So we use a midpoint method. Okay, so this midpoint, right? F at the midpoint, but I don't know what is xn plus 1, x plus half. So I make an estimate. So predictor. So so this is x plus half star. I use Euler forward, the delta t by 2. So this half here, delta t by 2, f at xn. Okay, so this is Euler forward. Euler forward. Okay, and this is a predictor step. Now I substitute it here. So corrector step is this. So I just substitute here, and I get xn plus 1. Okay, so this is second order accurate. Okay, so error is delta dq per step. Okay, and its stability region is exactly same as what we did before for predictor-corrector. And this is a code, pretty simple code really. So this is just pure setting up. But here I compute the midpoint, x mid by Euler scheme. So xk plus f at xk and tk dt by 2. And then xa, so this is a corrector scheme. Xk plus 1 is xk plus f at x mid. Okay. And t is, please remember, t is t plus dt by 2. Don't make a mistake that you put in the tk only. Okay. So this is the midpoint time at the midpoint. Okay. Often we have f which is independent of t. Okay. But sometimes it's function of t. If you have oscillator problem and you are forcing it, then it could be function of time, sine omega t also. So this is dt and done. So we can solve. So I strongly recommend that you should use RK2 for at least RK2. Don't use Euler forward, but use RK2. It is very easy to code and it gives you better accuracy. Okay, it's also stability is okay. I mean, stability is good. It is not as bad as Euler forward. Now RK4, which is more accurate, but is more work. So just to outline, so you compute xn plus half star for Euler forward k1, then use this one to again compute k2, and okay, so this again I computed the midpoint, right? This midpoint. So use this one again and compute now not at the midpoint but at the end point, xn plus 1. And then k4, we use this one to compute one more f. Okay, and so you got four of these k's, k1, k2, k4, and then this corrector. So xn plus 1 is this formula. Now it is accurate up to delta t4, and error is delta t5. So I recommend RK4. So RK4 is very popular for solving equations. Okay. And so what about its okay, stability? Stability is good again, x dot is alpha x. And we substitute here in this equation, we will get this. Okay. Now the boundary between stable and unstable region is given by this contour. And that contour, you can plot it. I mean, this is a contour plot, and this is a contour. Okay. Now it is bigger than this region, so you can use larger delta t. So for Euler backward, this was the region, but now I can use delta t twice, or not twice, but 1.5 times. So yeah, so your delta t must be within the region. Huh? But again, the same question comes. My equation is not as simple as this. Okay, this equation I don't need to use Rangakutta. I exactly know how to solve it. But for more complicated equation, it's not easy to draw this contours. Okay, so these are so a lot of engineering. It's like more of engineering. So well, it works for this delta t. It doesn't work for this delta t. So we have to go by trial and error. Okay.